So it looks like we have an audience here. What I'd like to do is introduce Dan Filimon. He popped up on the mailing list unannounced, just said, hey, is there something cool to work on? That was almost a year ago, 9 months ago. Turns out he's an undergraduate student. He was an undergraduate student. I guess that's a was now.
Still am now.
Still am. Yeah. At University of Bucharest. And he's done some excellent work over the last 9 months in getting this streaming k-means ready for inclusion in Mahout. We have a release coming up, and this is the centerpiece of that release in the new 0.8 Mahout. So I want Dan to give us a talk about how this stuff works.
Okay, thank you, Ted. So here's what we're going to be talking about. Basically, what data is, you probably all know that. Clustering, k-means, the problems with k-means, what we can do to address those problems, how do we do k-means to large scale, well, a bunch of stuff. Basically, this was actually a 70-slide talk initially. I tried giving this like a week ago. That failed miserably, so this is hopefully the short version that everyone will like and has more pictures. If you want to go and see the full version, it's there, that link, and obviously everyone will have these slides by tonight or tomorrow or whenever. Okay, so what is data? Well, data is anything you want. It could be like documents, web pages, images, users, but we don't really care about that. We essentially just want to have vectors, preferably real-valued vectors, but vectors with numbers in them. These are the feature vectors that you generate from the data in some way. You just encode it, and then we can cluster it. So what is this clustering thing? Well, we basically want to find some clumps in the data, I guess. The thing with clustering is it's not really one problem. Like, I'm going to talk about one way of doing clustering, but there are really more ways of doing it. And the one I'm going to be talking about starts with the following assumptions. You have these n data points, and they are in d-dimensional space, and you want to group them into k disjoint sets. So you want to do this, and the whole point of it is to minimize this total cost, which is this formula here, which is, I promise this is the only formula in the entire talk, okay, so it doesn't look intimidating, I hope. It's just, so the idea is these disjoint sets, we call them capital X, x1 all the way to xk, and xi is the ith cluster, ci is the centroid of the ith cluster. The centroid is just the mean of all the points in that cluster. And xij is the jth point from the ith cluster, and essentially what we're doing is we're summing up the distance from each point to its centroid, and summing all of those up, and that entire thing is called the total cost, and we want that to be minimized. So that's the problem that we're dealing with some distance metric. Like, the distance metric there is the L2 norm. It could be something else potentially, but a distance anyway. Okay, that was all of the math for today. So let me just show you how k-means works. So here are the points we want to cluster. So these are points, these are vectors. I use these words interchangeably. For now, they're points, right? They look like points. And say we want to cluster the data into 3 clusters. Now, the point here is that right here, you might not see 3 clusters. And indeed, in general, it might not be the case that you actually have k clusters. Sometimes you can't really tell how many clusters you want to have in advance. So you just pick some k, and we do it, and we'll see what it gets us, what kind of quality we can get there. So these points are in 2D space, and the first thing k-means does is pick some initial centroids. So say it's these guys. So we pick some points as the initial centroids. These aren't really the means of any clusters because we haven't computed any clusters at this point, but we just pick some points. In multiple, there are more ways of doing this, but we just pick some points. Let's just say they're these points, okay? And so the next thing we're going to do is, for each point, we're going to find the cluster that's closest to it, the centroid that's closest to it, right? And this will create this partition that you see there. I just made the partition up. Like, it might not be very accurate, but there you go. So this is the first iteration, and we're assigning each point to a cluster. And this is the assignment that we get. And so the first step is cluster assignment, and after that, we adjust the centroids. So the centroids were here, and the centroids are now there. They moved a bit. Okay, so after we do, this is one step, right? But we will probably do this multiple times. So the next step is this. So the assignment got changed a bit. Like, you can see the point there in the lower part of the screen change from being in the leftmost cluster to the other one, right? So there's that. That might not be very accurate, but let's just say it is. And then we adjust the centroids again. And you can keep doing this until, well, until you stop. And stopping is really you do it when when the code converges, basically, which is either for some number of iterations or no point changes cluster. We actually need to talk about these details. So first off, since the okay, for everyone who's done machine learning, this is an unsupervised learning problem, which means that we don't really know what the right answer is. The problem itself, as I defined it, is NP-hard, like the formula there, the minimization. So we can only do approximations here. And we define a bunch of metrics and say one of them is the total clustering cost, the thing that I talked about at the beginning, that formula, the sum. But there are others. In general, we want to have clusters that are compact and well separated. And there are a bunch of other indices that you can look up on Wikipedia, which measure this in some way. Like, they're not perfect, but better than nothing. So this is how we measure quality, and so we stop when quality reaches a certain level. Basically, that's one option, or after some number of steps. Then one of the biggest issues that we face that is like pretty much determines the quality is centroid initialization. So I told you that we're going to pick some number of points, the k points. We can pick them at random. That's the most straightforward thing to do. But there are some problems. If we pick them at random and we're really unlucky, like you see in that picture over there, we're going to get two seeds that are really close together in the same cluster, which will pretty much break everything. Because those clusters won't be able to be pulled apart, which will make one of them be empty at one point. So you get crappy clustering like that. So the clustering sort of fails in that case. And one typical way of addressing failures is just trying multiple times. So we can do multiple initializations. Or there's this fancy way of initializing called k-means++, where you actually take into account the distances between the points. You can look up more details in the other presentation, but for now, we just do random initializations as the most simple thing. Another issue is outliers. It turns out that real data is very messy, and sometimes you can't tell if some of the points should really be there or not. Those 3 points over there, they might be outliers, they might be a different cluster, who knows? But the thing is, assuming they are outliers, they're messing up that cluster over there, the one on the top right. So a better centroid, I think, would be the one where I pointed the arrow. But because of those 3 points, it got shifted down. So we'd like to avoid that. And one way of doing it is using ball k-means, which is basically just instead of using every single point in a cluster to recompute the centroid, you just use like a ball around the centroid. Wikipedia, basically, but it's not that complicated. Like, instead of doing that, you just say, make a ball around each of these. Imagine there's a ball, and it doesn't cover all the points. And for those that it does cover, you compute their mean. That's basically it. OK. So there's quality. We talked about these 2 issues, the initialization and the outliers. But other than that, we also care about speed. The main point of this project is so that clustering works faster. So what can we do about the speed? So first of all, what is the complexity of this? Well, the biggest thing that determines the complexity is really the cluster assignment, the part where we go through each point and through each cluster and compute the distance to that cluster, and then we take the minimum. So that's going to be n times. So if you have n points and k cluster, that's going to be n times k right there, and then times d for the distance calculation. So one way of getting a better speed is to simply not go through all the clusters. So we're going to reduce k. So instead of doing the accurate search, where you go through every single cluster, we're going to do an approximate search. Now, there are multiple ways of doing this, but pretty much everything we do is based on random projections. So random projections is basically a fancy name for a fairly basic idea. Here's a nice picture. So suppose that line is a vector. It actually is a vector, right? So we're talking about 2D space here, right? You basically are going to sample some vectors from a normally distributed distribution. You're going to normalize them, and you're going to get a direction. Say that is the direction. You're just interested in the direction really at this point. And it looks like a line if you want to think of it that way. Then you have those 2D points. And you can think of them as, so they're points, but they're also vectors, as in the other end would be in the origin of the system. And you can see how they project onto the line, right? So those are the projections of the vectors onto that direction. The cool thing about it is that it will give you a total ordering. So normally you have these d-dimensional vectors, you can't really compare them, right? You can't compare complex numbers, you can't compare these things. But if you project them, you will just have scalars that you can compare. And if you sort these, the cool thing is you can binary search. So you're given a new query vector that you want to search for, and you can simply search for it in this sorted set. And that's going to be a log k time operation. And there you go. You can actually get multiple directions if you want better quality results, but 2 or 3 works fine. So that's one approach. Like, there's a lot more detail in the other talk, but this is probably OK for now. So this is one approach that you can use to make it faster, and the other one is just, well, if the data is too big, like there are too many dimensions in these vectors, just make them smaller. And there are two, well, the one you probably have used is principal component analysis. And the other one is just have lots of random projections, and you can use those random projections, those vectors as a matrix, which will get you smaller vectors. The point is you apply linear algebra, and it just works. OK, that's basically it. OK, so k-means in Mahout does not do that. Like, it doesn't do any of that. It doesn't do the random projection search. You can potentially do it. It has SVD, so you can reduce D. But it doesn't do the smart initialization with k-means ++, doesn't do any of that. So what does it do? How does it work? Like, I've sort of explained to you what the basic algorithm is, but how does it look like as a map reduce? Because this is supposed to be a scale talk, right? So k-means as a map reduce is pretty much, well, first off, you want to parallelize it, right? You have the mappers and the reducers. You've all used map reduce. So the thing you would want to do is to split it somehow. But you have this outer loop, which is the number of iterations, right? You go through each iteration, and you do the cluster assignment, and then you do the readjustment of the centroids. But the problem is you cannot split the outer loop, right? Because you basically just have data dependency there, right? You need the results of the last step to do this current step. So that's a no-go. So you must express one actual step of the k-means algorithm as a map reduce, which basically just means that the mappers will be responsible for cluster assignments, and the reducers will update the centroids. Now, this works, as in this is exactly what Mahout does. And Mahout basically does what I just described with using random initialization and with some number of iterations until it converges. Now, so as I said, this works, but it's not ideal. We really don't like having multiple map reduces. For one, you shuffle more data around, you pass through the data multiple times. But then there's also the question of, well, you can't really do some things that you would really like for better quality clustering. So say you can't really do k-means ++, for instance. You do reservoir sampling to get the random points, but how do you get reservoir? K-means ++ is a lot more complicated than that. You need to dynamically adjust the probabilities of the points that you're sampling from. So we can't really do that. And so other issues are just like, in terms of implementation, we don't implement fast searching and stuff. So there's that. But we can use a totally different approach, though. And this totally different approach is not that totally different, it turns out. So if you went to the keynote, you already know what it is. It's basically just make large data into small data. So this is based on an idea in that paper. But there are multiple papers about this, but this is the one we actually use in the implementation, fast and accurate k-means for large data sets. The idea is, instead of clustering the large data set that you have, you want to cluster a smaller one, right? So what you want to do is to build a sketch of the data. A sketch of the data is basically just you want to do a clustering, but with more than k points probably, and each cluster that you're going to have, each intermediate cluster is going to be a representative for the points in that cluster, each intermediate centroid, sorry. So in the paper, it basically says that you need to have O of k log n intermediate clusters for there to be any sort of guarantees about what the k clusters you're going to get at the end will be like. And the key idea here is we want to collapse these clusters so that the resulting data set will fit into memory, because we can do a lot more things when we have the points in memory. But here's what streaming k-means looks like. Here's what it does. So streaming k-means is an online algorithm, right? That's the entire point. That's why we can do just one iteration through the entire data set and still get the clusters. So here's what it does. So you have the first point, which comes in. There's no other centroids, so you might as well make it a centroid, right? Then you get another point, which is fairly far away, say. Now, this point being that far away, it will become a centroid because, well, it seems fairly far, so it sort of makes sense. It's just intuitively points that are really far from a centroid should be centroids, right? Then you get another point, which is fairly close to the closest other centroid that you have. So being fairly close, we're going to say, well, this is close enough, so rather than making this a new centroid, we're going to just put it in that cluster. So the cluster becomes these 2 points, and their centroid is that red dot that moved a bit. So we merge it in that case. Now we get another point. This point is fairly close, right? It's fairly close to the red cluster, to the closest cluster. But you see, here's the part that's nice, because we could merge it, but then it turns out that here we don't merge it. We make another centroid. Now, there's no real reason for this. It's more of a probabilistic choice. So the main idea here is that as points are further from their closest centroid, they should probably be a separate centroid themselves. If they are close enough, then they will, with some probability that increases as the distance decreases, they will be part of that cluster that they're close to. So this is the pseudocode. This is like the horrible slide with the text in it. The basic thing that you want to look at here is this chunk, then if an event with probability proportional to blah, blah, blah occurs. The idea there is that that's where you compute the distance, right? The distance to the closest cluster. And if that is close enough, then we will want to add it to the cluster. Otherwise, we're going to create a new cluster. And you can see that there's a weight, the W there included. And what that's saying is, well, if there are lots of points in that cluster represented by that centroid, we're actually okay with not really making it with not really merging it, because we would sort of lose too many points. We're clumping stuff together, which we shouldn't really be doing. And okay, we did that, but you're getting points one by one, like I've shown you in the other slides. You're getting points one by one, but you're going to be making lots of clusters, right? You need to stop at one point, because we said we want to have O of k log n. So when do we stop? Well, we don't really stop. We just continue going on until we have too many clusters. Now, this too many is fairly loose. You can look at the paper, the code, but basically it's supposed to be within some constant of that k log n. And when that happens, what we're going to do is, instead of, we need to collapse them somehow, right? There are way too many of them. So we're just going to do another pass of the streaming k-means. But instead of adding new data points and clustering those, we're going to use these centroids that we have that are way too many. We're going to treat those as points, and we're going to just collapse those together. So that's what we just applied recursively, sort of. So that's streaming k-means, basically. Now, what this allows us to do is, this allows us to do just one pass through the data, which is really useful. And how would this work with, the big MapReduce idea? Well, the idea is you have all of your points, right? And instead of having that problem with the outer loop that you can't split, you don't care about that anymore. You can just get all of the points, and you're going to split them across your mappers. You're going to run streaming k-means on each mapper. They're going to get some intermediate centroids from every single mapper. And what you want to do with those is you're going to collect them in just one reducer. And you might potentially apply streaming k-means again if there are way too many of them. But there should be enough points so that they fit into memory, right? That's the main idea. And once you get few enough points, then you're going to be able to just apply bulk k-means. And bulk k-means just basically the ordinary k-means we talked about previously, with some fancy tricks like the k-means plus initialization, which you can do because the points will fit into memory this time. So you just do that in the reducer, basically. And that gives you the approximate k-means, basically. That's how you get the k-clusters. Now, this is for MapReduce, right? You can also do this in Storm, sort of. So how many of you have used Storm? Do I need to tell you about what it does? Yeah, have you used Storm? Okay, 2 people? 3 people? Okay. So basically, in Storm, you have this network of nodes, which you call bolts. And you build this network of these nodes, basically. And you start from points called spouts. So those emit the data that goes through this topology, the graph, right? And in each node of the graph, you're processing those streams somehow, the streams of tuples, the data that's coming through. Storm is supposed to do online processing. So what we can do for Storm is, as our points are streaming in, like literally streaming in, streaming k-means makes a lot more sense. It's not doing batch processing as MapReduce does. So we can just do streaming k-means in one bolt, where each point comes in through the bolt. We're going to cluster it with what streaming k-means does, and periodically, or based on some signal or something, we're going to emit the approximation that we have. That's basically the use case. And you can do that. You can do anomaly detection or stuff using this. But the code to actually do this, I have it, it's in a GitHub repo. It's just you copy in the Mahout code and change a few things. It works fairly well. And so and there's Trident, which is basically a higher level Storm thing, but I'm not going to go there. So now that I talked to you about all that, how does this actually perform? Well, let's set our expectations straight, I guess. So what we want to do is we want to get something that is approximately the same as k-means, right? Both of these are approximate algorithms. So it's not as if you're going to get the optimal solution or anything, but ideally, with this other approach, since it's supposed to go faster, that's the main point. We want it to also have decent quality. So we're going to compare the quality and the speed. Now, what I did for measuring the quality is I picked these small data sets off UCI. If you do machine learning, you've probably seen these already. Some of them are really small, like Iris has just 150 points with 4 dimensions each. These are just Iris species. But then there's Power, which is like a lot larger, has like 22 million points with 9 dimensions. But still, these fit in memory on just one machine, so they're not very big. And what I did to compute the quality here is simply compute the total cost, which is the thing that we mentioned that we want to minimize. So that's good if that's small. But also these 3 measures that you see there, the Dunn index, the Davis-Bolt index, and the adjusted rand index. So what these do is the first 2 basically try to tell you if your clusters are compact and well separated. That's essentially it. I could put the formulas on the slide, but you can just go to Wikipedia and see what they look like. The idea is for the Dunn index that you want it to be large, and if it's large, then that means you have a good clustering. And the Davis-Bolt index is supposed to be small. Now, the adjusted rand index, on the other hand, is supposed to be a measure of the similarity of 2 clusterings. So say you have 2 20 clusterings, right, of the same data. And what you do is, so I'm going to just switch to the next slide, which is an actual example here. So this is the Iris data set, right? The small 150-point example. So you build this matrix table called the confusion matrix, or if you've done classification, this is probably familiar. So what you do is for each example that you have, you're going to find the closest clusters that it's closest to, right, in the 2 clusterings, in clustering 1 and in clustering 2. And so suppose it's closest to cluster I in clustering 1 and cluster J in clustering 2. Then you're going to go to cell ij in this matrix and increment that by 1, by that point. And then you simply do that for every single point that you have, and you compute the total cost, and you're going to get a matrix that looks something like this. So what this matrix tells you is that the clusterings are fairly similar, right? Because so ball and streaming k means that new approach is the columns, and Mahout k means what we had initially is the rows. So if you add up the rows, you're going to get the number of points in the Mahout clusters, in the k-means clusters. And if you add up the columns, you're going to get the ball streaming k-means clusters. So you can see that cluster 2, for example, in Mahout has 51 points in it. And that's exactly the same as cluster 1 in ball streaming k-means, right? And then you can see that, oh, if you look at cluster 1 in Mahout k-means, that has 38 points. And in ball streaming k-means, cluster 3 has 38 points. So you can see that they might be permuted, but they're the same, right? You have the exact number of clusters. So this is why the adjusted rand index is 1 in this case. The adjusted rand index goes from 0 to 1. And you can think of this as sort of like the percentage in which these things are similar. That's just an intuitive idea of what these things do. And so in this case, you got the exact same clustering. Hooray, right? It worked just fine using just 1 pass. Now, I actually did 5 runs of this to see how it works. And it sometimes doesn't work that well for Mahout's k-means, for just normal k-means. And the problem is in this confusion matrix, you're seeing the effect of a poorly chosen seed. So look at the first cluster in Mahout k-means. That basically has the second and third ball and streaming k-means clusters lumped together. So it's 38 plus 59 points put in the same cluster. That's probably because of a seed that was picked, by the random sampling. You can't really do anything about this other than run the algorithm again and again until you get this. Now you're not going to always get the perfect clustering, exactly the same clustering, but here you go. So this would not ever happen for a ball streaming k-means just because you're doing the smarter sampling. So there's that. At least we're not prone to that problem, right? Okay, then I have a box plot. This is for the seeds data set. And so this basically plots the distribution of distances within each cluster, right? And it sort of like plots that across all of the runs, all of the 5 runs. So the black bars are like the median of that distribution. So you see BSKM is the ball streaming k-means thing, and KM is the k-means thing, right? You can see that they're fairly similar, and also the means are pretty much the same, 4.3 versus 4.2. So the average distance is pretty much the same, and even the distributions look fairly similar. Now this is probably pretty hard to visualize, so there's this other plot for some other data set called movement. This actually shows you for all 5 runs what the distances in each cluster look like. Well, the average distances anyway. So you can see that they tend to look fairly similar, right? Like k-means and ball streaming k-means. Now the empty circles are ball streaming k-means and the full ones are k-means. So you can see that they're pretty much, about centered around the mean, but then there's also some outliers. Say in the second run, in the red run, there's a red k-means dot like way up there. This just happens. Like, it doesn't happen all the time. And the first 2 runs, I think, look pretty similar. And in this case, actually, ball streaming k-means is actually a bit worse. It has mean distance 1.5 rather than 1.4 something. Here's another confusion matrix, but this is for a data set that's not as easily clusterable. So the thing is, you have your data and you want to cluster it, right? But you're probably not going to get, it doesn't really make sense to cluster it sometimes, or it doesn't make sense to cluster it with as many clusters as you want it to. So sometimes you're going to get totally random distributions of clusters. Although you can sort of see that Mahout k-means tends to split up the clusters to some extent. Like say cluster 3 in ball streaming k-means is split across clusters 3, 4, and 5. Anyway, in this example, the adjusted rand index, that measure of similarity between the 2 clusterings is only 0.7, so not as good. So basically what I'm saying here is that if the data itself isn't as easily clusterable, like there aren't exactly how many clusters you wanted, say the 20 clusters aren't really there, then that basically means that the 2 algorithms will sort of diverge in what clusterings they'll get you. But that's just, I mean, if you actually have like the 3 clusters that we had here, they do agree. But if the data isn't clusterable, not so much. Okay, now here's another all plot. Well, I gave these really crappy names. This is another plot for the power data set. This was somewhat larger. This one is neat because, first off, you can see that the median for k-means is a lot smaller. But then you have those dots at the top, which are the outliers. So you have like some points, some clusters have really large distances. Also, the y-axis is log scaled, so those are very large. And these just look very similar, very dissimilar. So you might think that k-means is actually doing a better job here, but we'll see. And here's basically another one that's for the exact same distribution for the same data set as this one, as power. And you can see the outliers on this one as well, like the blue and green ones, the blue and green runs especially, right? And the means are pretty much the same here. Okay, so I showed you all those pretty pictures, but to summarize in a table, the bold results are better. So if the Dunn index is better, that's bold. If the Davis bold index is bold, that's better. So you can see basically that for the 2 first ones, the iris and seeds, the clusterings are fairly similar. Like you have 0.98 and 0.9 adjusted rand index, so they do agree to a large extent. On the other hand, though, it's funny because the done index for iris is 9 point something, but for ball streaming k-means is just 6 point something. This actually goes to show you that these indices tend to be deceiving sometimes. It's that large because in this case, where it actually gave you really crappy clustering, the done index of this is actually really large. So, all of these indices should probably be used with some skepticism, I guess. You should probably just use more metrics to see if the clustering is really good or not. So yeah, that's why you have a 9 point something there. But for seeds, you get fairly similar results. And you can see that ball streaming k-means is slightly less good, right? Like these quality indices are slightly worse. Except for iris, again, the average cost is less because of that mistake that k-means made because of the faulty initialization. But interestingly enough, once you get the larger data sets, particularly control and power, you can actually see that something really weird is happening, at least in power. Like ball streaming k-means is a lot better than k-means. I am not sure why this is really. It should be fairly similar, but I just guess that, k-means probably got unlucky with some initializations, and that was just it. So, and you can see that for these last 3 data sets, the clusterings don't really agree. Like you just have a 0.6 average rand index, so yeah, not as clear cut what the clustering should be. Okay, now then, that's the quality. I hope at least that I sort of convinced you that the quality of this approach is the same or maybe sometimes better, but basically the same. Now on to the main reason of implementing this, namely speed. So what is the speed like? So first off, here's the speed for the threaded version of streaming k-means. This plots the time to cluster 1 point versus the number of threads. And you can see that the speed up is nearly linear. And so that's basically as good as it gets, right? It scales linearly across as you get more threads here. Well, and of course, assuming you have the cores. Okay, so this is a threaded example, but still not really large enough. We talked about MapReduce, that's what we wanted to do. So for MapReduce, I needed a larger data set, which I generated myself, which is probably, not the best idea, I guess, since it was fairly small anyway. So what I did was I got, say, 120 million on that order of magnitude points that have 500 dimensions that I sampled from the corners of a hypercube. It was just a multinormal distribution in each of the vertices, and I simply got 20 of them that were the actual clusters that I was supposed to be getting, and I just sampled from those, basically. And yeah, you have like 120 million points, which is like 7 gigabytes of data on a 4-node cluster. It was initially a 5-node cluster provided by MapR, but I messed up and killed 1 node, and I don't know how to start it up again. So 4-node cluster. And this is what the performance looks like. So this is a case where you want to have 20 clusters. The gray bars are k-means. And you can see that it needs 3 iterations to converge, right? 3 MapReduces. And each of them takes 20 minutes, whereas streaming k-means takes 25. So it's like a bit longer than that. So the reason here is that 20 clusters isn't really that many clusters. So you won't really get any advantages from the nearest neighbor search that you're doing in streaming k-means. And also there's the issue of, well, you're also doing more things in the streaming k-means job. You're doing the streaming k-means and you're doing the bulk k-means at the end. And actually, we're not really just doing one bulk k-means, we're actually doing multiple initializations there, and we're trying to get the one that has the best cost. So it's actually doing more things there. But still, it's basically the same as one iteration of Mahout's k-means. So this is pretty good. Now, 20 clusters, again, isn't that much. So what if we go to, say, 1,000 clusters? This is where k-means not doing any sort of fast search kind of breaks down. This is where Mahout's k-means kind of doesn't do the right, well, it does do the right thing, but is very inefficient. So for this case, with 1,000 clusters, you can see that it finishes in 2 iterations, right? Which is because you're asking for 1,000 clusters when you really only have 20 clusters. So it'll figure out what the assignments should really be fairly quickly. But streaming k-means, on the other hand, it finishes what Mahout k-means did in 4 hours and 30 minutes. So that's like 8 times faster. And also, just one iteration is a lot faster too, just because it's doing the approximate nearest neighbor search. So yeah, there's that. And basically what the conclusion of all this is, you can have essentially the same quality of the clusters, and it's a lot faster. Like it should be at least as fast as one. It should be about as fast as one iteration of Mahout k-means of the basic one. But if you have lots of clusters, then it's going to be a lot better. So okay, I hope I convinced you about that. And the code is in Mahout right now. It's going to be part of the 0.8 release, so you can start playing with it. These are just a few classes. So bulk k-means and streaming k-means are like the main classes that do the clustering. Then there's a bunch of fast nearest neighbor searchers, like projection search, for example. And then there are some quality metrics that calculate all of these indices that I talked about. And of course, the MapReduce classes. And there is a Storm prototype on GitHub, which you might use, but then it's sort of like, I mean, I'm not going to guarantee that that works properly. So, okay, that was it. If you have any questions, hope you do have questions, because I sort of skipped over lots of slides, well, in the full one. Okay. So questions?